Hello friends, today I am available with a new video related to air standard dual cycle with numerical as well as comparison of Otto cycle, diesel cycle and dual cycle. So please go through this video. This will be helpful to you for your internal test, for your university exam as well as for your competitive exam. If we'll compare dual cycle with Otto cycle and diesel cycle, we'll find that in case of dual cycle, the energy is added into the system at constant volume as well as at constant pressure. Otherwise, all the processes are similar to that of Otto cycle and diesel cycle. So important thing here is the heat which is added, that is heat addition part, is observed at constant volume as well as at constant pressure. Remaining things are same like Otto cycle and diesel cycle. You can see the diagram, that is a PV diagram and TS diagram for the dual cycle, where you will observe 1 to 2 process is a process of compression, 2 to 3 and 3 to 4 is the process of heat addition, where you can see the process 2 to 3, that is the constant volume heat addition, as well as 3 to 4 is the constant pressure heat addition process. Otherwise, you will observe process 4 to 5, that is expansion process, that is a power stroke, and 5 to 1, that is, you can say, exhaust stroke, where the exhaust product will leave the engine cylinder, and the same thing you will observe on the TS diagram. So only important thing which you can see here is process 2 to 3, that is the constant volume heat addition, whereas process 3 to 4, that is the constant pressure heat addition process. Now we have to find out what is the efficiency of dual cycle. So like diesel cycle, what we have to do is we have to convert all the temperature into the T1 temperature, and then after we will get what is the efficiency of dual cycle. So initially we have to find out what is the heat added. So Q1, that is equals to CV, that is the constant volume part, that is CV into T3 minus T2 plus Cp into T4 minus T3, that is heat addition at constant volume as well as at constant pressure. Cv, that is a specific heat at constant volume, whereas Cp is the specific heat at constant pressure. Similarly, the heat rejected, that is Q2, that is equals to Cv into T5 minus T1. So that is heat rejection that is observed at constant volume. So now efficiency, that is equals to 1 minus Q2 by Q1, that is 1 minus heat rejected divided by heat supplied, that is equals to 1 minus Cv into T5 minus T1 divided by Cv into T3 minus T2 plus Cp into T4 minus T3. So we can simplify it by efficiency, that is equals to 1 minus T5 by T5 minus T1 divided by T3 minus T2 plus gamma, that is adiabatic index, which is a ratio of Cp by Cv into bracket T4 minus T3. That is our equation for efficiency. And now we know that compression ratio, that is Rc, that is V1 by V2, cutoff ratio, that is RCO, that is V4 by V3, expansion ratio Re, that is V5 by V4, and pressure ratio Rp, that is P3 by P2. So now we have to use all these ratios and we have to find out what is the efficiency. So you can see Rc, that is cutoff ratio, that is V1 minus V2. We can multiply it and divide V4 on both the side. So we will get V1 divided by V4 into V4 divided by V2. Now we know that V5, that is equals to V1, that is a constant pressure, constant volume expansion process. So V1 is replaced by V5. So V5 by V4 into V4 by V2. And so cutoff ratio Rc, that is equals to RCO into Re, that is compression ratio Rc, that is equals to cutoff ratio into expansion ratio. So here you can see Rc, that is compression ratio, that is a multiplication of cutoff ratio and expansion ratio. Now for the process, what we have to do is very much clear to us. We have to convert all the temperatures into T1 temperature. So T5, T3, T2, T4 and T3, all the temperature we have to convert into T1 temperature. So now we will start the process to convert all the other temperature into T1 temperature. So the first task is for process 1 to 2, that is isentropic compression process. T2 we have to find out in terms of T1. So T1 by T2, that is equals to V2 by V1 raised to gamma minus 1, and from that we will get T2, that is equals to T1 into compression ratio raised to gamma minus 1. Similar way, for process 2 to 3, that is a constant volume process, we will get T3 by T2, that is equals to P3 by P2, that is Rp, and we will get T3, that is equals to T1 into Rc, that is a compression ratio raised to gamma minus 1 into pressure ratio. In the same similar way, for the process 3 to 4, we will get T4 temperature, that is equals to T1 into Rc, that is compression ratio raised to gamma minus 1 into pressure ratio into cutoff ratio. So friend, here we try to convert all the temperatures into T1 temperature for simplification, and we will get efficiency of dual cycle. So now for the process 4 to 5, that is isentropic expansion process, we will get T5, that is equals to T1 into compression ratio raised to gamma minus 1 into pressure ratio into cutoff ratio into bracket cutoff ratio divided by compression ratio raised to gamma minus 1. So we will get T1 into RCO, that is cutoff ratio raised to gamma into pressure ratio. So now all the other temperatures are converted into T1, and we have to put all that values in the equation of efficiency. So efficiency, that is equals to 1 minus T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. Now we are replacing all the other temperatures as a T1 temperature. So the last equation 5.26 is available with us, and now upon simplification what we will get that we will see in the next slide. So now the efficiency of dual cycle, that is equals to 1 minus cutoff ratio raised to gamma into pressure ratio minus 1 divided by compression ratio raised to gamma minus 1 into bracket pressure ratio minus 1 plus gamma into pressure ratio into bracket cutoff ratio minus 1. So in this equation, if we'll put cutoff ratio, that is equals to 1, efficiency of dual cycle, that is equals to the efficiency of Otto cycle, and if we'll put pressure ratio equals to 1, in that case we will get efficiency of dual cycle, that is similar to the efficiency of diesel cycle. Now the next task is to find out mean effective pressure. So the mean effective pressure, that is PM, that is equals to net work divided by V1 minus V2. So our first task is to find out what is the net work done, and second task is what is the swept volume. So we will move towards our first task, that is net work done, that is equals to heat supplied minus heat rejected. So that is equals to CV into T3 minus T2 plus CP into T4 minus T3 minus CV into T5 minus T1. So and the swept volume, that is V1 minus V2. So we will keep V1 common. So we will get V1 into 1 minus V2 by V1. And V1 is equals to RT1 divided by P1. So we will get that swept volume equals to RT1 divided by P1 into bracket 1 minus 1 upon compression ratio RC. So that is equals to RT1 divided by P1 into RC into bracket compression ratio minus 1. So when we will go for simplification, we will get mean effective pressure, that is equals to CV by R into P1 into RC into bracket gamma minus 1 divided by into bracket RC minus 1 into square bracket RC raised to gamma minus 1 into bracket RP minus 1 plus gamma into RP into RC raised to gamma minus 1 into bracket cutoff ratio minus 1 minus RC raised to gamma minus 1 into RP minus 1 bracket complete, where CV by R, that is equals to 1 upon gamma minus 1. Equation number 5.27, which we can see, that is a equation to find out mean effective pressure for dual cycle. In above equation, if cutoff ratio, that is equals to 1, mean effective pressure for dual cycle, that is similar to mean effective pressure for Otto cycle, and if the pressure ratio is equals to 1, in that case mean effective pressure for dual cycle that is similar to mean effective pressure of diesel cycle. So this is about theory related to dual cycle. Now we have to solve simple numerical related to dual cycle. So now friend, based on working of dual cycle, we have to solve numerical. So we'll solve one sample numerical in which we will calculate everything what we had discussed in the previous theory. So in the data it is given that an air standard limited pressure cycle has compression ratio of 16 and compressor begins at 0.11 megapascal and 115 degrees Celsius. The maximum pressure of the cycle is 6 megapascal and maximum temperature of cycle is 2000 degrees Celsius. Calculate first heat supplied at constant volume, second heat supplied at constant pressure, next work done, then cycle efficiency, then temperature at the end of constant volume heating process, cutoff ratio and mean effective pressure of the cycle. So in this numerical we have to find out everything what we had discussed in previous theory, including cycle efficiency and mean effective pressure. So now we will start the solution of this numerical. So first we have to draw the PV diagram for the system where you can see the cycle, that is 1, 2, 3, 4, 5, 1, where heat is supplied at constant volume as well as at constant pressure. In the data, compression ratio is given, that is 16. P1 pressure is given 0.11 megapascal, that is 110 kilopascal. T1 temperature is given 115 degrees Celsius, that we are converting into Kelvin, that is 388 Kelvin. The P3 pressure, that is equals to P4 pressure, that is equals to 6 megapascal, that is highest pressure, that is 600 kilopascal. T4 temperature is given 2000 degrees Celsius, that is 2273 Kelvin. So now we start to calculate all the pressures and temperature at all the points of the cycle. So first part is heat supplied at constant volume. So for the process 1 to 2, we know that P2 by P1 that is equals to V1 by V2 raised to gamma. So from that we will get P2 value, that is equals to P1 into V1 upon V2 raised to gamma, where P1 is 110 kilopascal and V1 by V2 that is 16. Gamma is adiabatic index, that value is 1.4. So we'll get P2 pressure, that is equals to 533.5 kilopascal. Similarly, T2 temperature, that is equals to T1 into V1 upon V2 raised to gamma minus 1. So T1 temperature is known to us, 388, and V1 by V2 is known to us, that is 16, and gamma minus 1, that is 1.4 minus 1. So T2 is 1176.2 Kelvin. So P2 and T2 values are available with us. Now for process 2 to 3, T3 that is equals to T2 into P3 by P2, where T2 value is known to us and P3 and P2 values are available with us. So we can calculate the value of T3 temperature, that is 1322.8 Kelvin, and based on that heat supplied at constant volume, Q1 at constant volume, that is equals to CV into T3 minus T2. T3 and T2 that values are calculated, and based on that heat supplied at constant volume, that is 104.67 kilojoule per kilogram. The second task is heat supplied at constant pressure. So heat supplied Q1 at constant pressure, that is equals to Cp into T4 minus T3, that is 1.005. T4 that is 2273 and T3 that is 1322.8. So based on that we will get heat supplied at constant pressure, that is 954.95 kilojoule per kilogram, and based on that the total heat supplied Q1 that is equals to Q1 at constant volume plus Q1 at constant pressure. So when we add that two heats we will get the total heat supplied, that is 1059.62 kilojoule per kilogram. So friend, our second task is to find out work done. So for process 3 to 4, we know that V4 by V3 that is equals to T4 by T3, we know what is the values of T3 and T4. So based on that, we will get V4, that is equals to 1.718 V3. And from process 4 to 5, we know that T5, that is equals to T4 into V4 by V5 raised to gamma minus 1. So when we will replace V4 by V3, in that we have to put V4, that is equals to 1.718 into V3 divided by V1 raised to gamma value is known to us, that is 1.4 minus 1. And when we will calculate, we will get T5 temperature, that is 931.02 Kelvin. Based on that, heat rejected, that is Q2, that is equals to CV into T5 minus T1. So that answer is 388.8 kilojoule per kilogram. And based on that, W net, that is heat supplied minus heat rejected, or you can say total heat supplied minus total heat rejected. So that is 1059.62 kilojoule per kilogram minus 388.8 kilojoule per kilogram. So we'll get the answer, that is equals to 670.81 kilojoule per kilogram. That is the work done available from the system. So now we will move towards the next task. So cycle efficiency is the ratio of net work available divided by supplied heat. So net work which is calculated, that is 670.81 divided by total heat supplied, that is 1059.62, and based on that we will get efficiency of dual cycle, that is 63.33%. Now our next task is to find out the temperature at the end of constant volume heating process, that is T3, and that value is known to us, that is 1322.8. Now the next task is to find out cutoff ratio. So cutoff ratio, that is RCO, that is equals to V4 by V3, that is T4 by T3, and that value is 1.718. And the next task which we have to discuss, that is in next slide. Now we have to find out what is the mean effective pressure of the cycle. So it's state 1, P1 V1 equals to RT1. So based on that we will get the value of V1, that is equals to 1.0123 meter cube. And now compression ratio RC, that is equals to V1 by V2, that is 16. So we'll get what is the V2 value, that is V1 by RC, and that value is 0.0636 meter cube. So based on that, mean effective pressure, that is equals to W net divided by V1 minus V2. So W net is available, that is 670.81, whereas V1 minus V2, that is calculated. So based on that, we will get mean effective pressure of the cycle, that is 706.78 kilopascal. So friend, this was one sample numerical related to dual cycle, where what we had discussed to find out all the properties at state 1, 2, 3, 4, 5. Then we had calculated what is the total heat supplied, that include heat supplied at constant pressure and heat supplied at constant volume. Also we had calculated what is the value of work done, what is the value of heat rejected. Based on that we had calculated what is the efficiency of dual cycle, plus at the end we had calculated what is mean effective pressure of the cycle. So friends, if you follow these steps, definitely in the exam you can easily calculate the different questions which are asked to you based on dual cycle. So now our next task we will discuss. Friends, now we have to discuss a very important point, that is comparison of Otto cycle, diesel cycle and dual cycle. There are important factors based on which we can give the comparison between all these air standard cycle, that include compression ratio, peak pressure and heat addition. So when we are going for comparison between Otto cycle, diesel cycle and dual cycle, the comparison of these three cycle is made up for same compression ratio, same heat addition and constant maximum pressure and temperature. And this analysis will tell at the end that which cycle is more efficient compared to other two for a given operating condition. So now we will consider first case where we will consider same compression ratio and same heat addition. So when we'll go for same compression ratio and same heat addition, what is the effect of this compression ratio and same heat addition on Otto cycle, diesel cycle and dual cycle, that we will analyze based on PV diagram and TS diagram. So in the PV diagram, you can see the Otto cycle is represented with 1, 2, 3, 4, 1, whereas diesel cycle is represented with 1, 2, 3 dash, 4 dash, 1, and the dual cycle is represented with 1, 2, 2 double dash, 3 double dash, 4 double dash, 1. Now you can see in the TS diagram that the area under the curve 5, 2, 3, 6, that is equals to the area 5, 2, 3 dash, 6 dash, that is equals to area 5, 2, 2 double dash, 3 double dash, 6 double dash, as this area represent the heat input, and the heat input for all the cycle remains same. So you can see in the TS diagram that all the cycle that will start with the same starting point, that is initial point, point 1, and 1 to 2 is the compression process that will be observed same in the PV diagram for all the cycle. But when you refer the TS diagram, you can see for the same heat input, the heat rejection in Otto cycle is minimum, whereas the heat rejection in case of diesel cycle is maximum. The Otto cycle is represented with the area 5146, whereas the diesel cycle is represented with the area under 514-6-. So heat rejection in case of Otto cycle is minimum, whereas heat rejection in case of diesel cycle is maximum. Whereas the Otto cycle has highest work output and efficiency, whereas the diesel cycle has least efficiency, and dual cycle is falling in between the Otto cycle and diesel cycle. One more observation which you can see in the PV diagram, that Otto cycle allows the working medium to expand fully, that is between 3 to 4, whereas in case of diesel cycle there is a least expansion is allowed of the working substance, that is between 3 days to 4 days. And because of that, when the working substance is expand fully, more power is available, and because of that we can see the Otto cycle is having highest work output and efficiency, diesel cycle is with least value, whereas the dual cycle is having the values in between the Otto cycle and diesel cycle. So based on the PV diagram and TS diagram, what we had concluded, same thing is mentioned here. Just go through this. So what we had discussed, Otto cycle is having highest efficiency and work output. Second number is of dual cycle, and the last number is of diesel cycle. So just go through this. So what we had concluded, same thing is mentioned here. We will consider the second case, that is comparison of Otto cycle, diesel cycle and dual cycle for same compression ratio and same heat rejection. So here you can see the PV diagram and TS diagram for Otto cycle, diesel cycle and dual cycle for same compression ratio and same heat rejection. So we know that efficiency of Otto cycle, that is equals to 1 minus heat rejected divided by heat supplied. And if you refer the TS diagram, you can refer the amount of heat supplied in case of Otto cycle, that is shown with the graph or with the curve 2 to 3. The process 2 to 3 is heat addition process. And if we talk about diesel cycle, the efficiency of diesel cycle, that is equals to 1 minus heat rejected divided by heat supplied. So you can say that is equals to 1 minus QR upon Q dash S. So the amount of heat supplied by the diesel engine, that is represent under the curve 2 to 3 dash in the TS diagram. So 2 to 3 is the amount of heat supplied in case of Otto cycle, whereas 2 to 3 dash is the amount of heat supplied in case of diesel cycle. So from this TS diagram, it is very much clear that the amount of heat supplied in the Otto cycle is more compared to the diesel cycle, and because of that, efficiency of Otto cycle is definitely higher than the diesel engine for the same compression ratio and same heat rejection. And because of that, efficiency of Otto cycle is more than efficiency of dual cycle, and efficiency of dual cycle is more than efficiency of diesel cycle for the same compression ratio and same heat rejection. So friend, what we had discussed about efficiency for Otto cycle, diesel cycle and dual cycle for the same compression ratio and for the same heat rejection, that is shown here in the description. Just refer the description. So what we had concluded, that is very much clear to you. Now friend, again we'll compare the Otto cycle, diesel cycle and dual cycle with the third way, that is same peak pressure, same peak temperature and same heat rejection. So in that case you can see the figure A and B, that is of PV and TS diagram for Otto cycle and diesel cycle. You can refer the cycle 1, 2, 3, 4, 1, that is Otto cycle, whereas for dual cycle you can say the cycle is 1, 2, 2 days, 3, 4, 1. Now if we talk about the efficiency of Otto cycle, that is 1 minus QR upon QS, whereas for diesel cycle the efficiency, that is equals to 1 minus QR upon Q dash S, where Q dash S and QR both are nothing but heat supplied. Here the maximum pressure, maximum temperature and the amount of heat rejection are same, and based on that you can refer the TS diagram. From the TS diagram you can see the area under the curve 2 to 3, that is the amount of heat supplied for Otto cycle, which is lesser than the amount of heat supplied by the diesel engine, which is represented with the curve 2-3, and because of that the efficiency of diesel cycle is more than that of Otto cycle when we will consider same peak pressure, same peak temperature and same heat rejection. So efficiency of diesel cycle is highest, then dual cycle, then Otto cycle. So diesel cycle efficiency is highest, second number is dual cycle and third is Otto cycle. So now we will refer the description which is mentioned. So the theory which we had discussed based on PV diagram and TS diagram, same thing is mentioned here. Just refer the discussion, and the last line indicate that efficiency of diesel cycle is highest, second number is of dual cycle and third number is of Otto cycle. So friends, this was about basic of dual cycle with numerical and comparison of Otto cycle, diesel cycle and dual cycle, which is helpful to you to your competitive examination as well as your class test and the university exam. Do not forget to subscribe, like and share this channel. Also, if you have any suggestion, do not forget to put your suggestion. Have a nice day. Thank you.